afternoon. As always, when you prepare a presentation like this, you start with, we don't have enough content, we need more. And now we got to the stage where like, oh, let's delete this, we've got too much, let's hurry up, let's keep the intro short. So that's what I'm gonna do, I'm gonna keep the intro short, just quickly make...
As long as you've left all the solid tech stuff in there.
Exactly, so that's why we're keeping the intro short. Just to make sure, because I see just a few faces that I haven't met before, I just want to make sure that you guys are familiar with who we are and what we do. Here you can see a quick overview of the agenda. So after the overview, we're going to talk about server SAN and the benefits of server SAN. We're going to dig into the industries and applications where this is useful. And then the big thing for today, the premiere that you're getting is a demonstration of NVMesh for containers or container environments. We'll also dig into the architecture of NVMesh a little bit. And then we're gonna end it up with a little bit of myth busting. And one of you is partly responsible for this section. All right, so technology, love it. Our company, Excelero, was founded originally in Tel Aviv, Israel. Right now we're headquartered in the US. We're pretty global. Marketing sits in Europe, that's myself. We're about 40 people. We're funded, pretty well funded. One of you made an accurate statement that we're funded at 23 million right now. In our round B, Battery Ventures took the lead. One of our angel investors, not unimportant to mention, is David Flynn. We just got one patent granted and we've got 10 more pending, and the markets that we serve we will talk about later on because there's some more interesting slides to talk about that. The market trends that we've been responding to is, first of all, the market is asking for a paradigm shift to shared accelerated storage. A second trend that we're responding to is the growth of NVMe in the market. More and more companies are seeing the benefits of moving to NVMe. One global bank that I was talking to was the senior VP of storage. He told me that he expects actually that was a year ago, so within a year he expects all their flash to be replaced by NVMe and all their regular disks to be replaced by flash. Now, to what extent that's really going to happen that fast, we don't know, but it's really a good indicator of the industry expecting NVMe to take over very quickly. We're also leveraging network innovations, including RDMA. And very important for us is the acceptance of server SAN. And server SAN is, we've seen it in object storage where companies, one company that's been talking here or will be talking here later on, talks about object storage on standard servers. We're doing exactly the same for SAN, which is a little bit more complicated, but gives a little more, or much more benefits actually. All right. The reason why we're doing what we're doing is we were inspired by the big five, Facebook, Amazon, Google, who have all been building data centers that need to be very efficient, very flexible, using standard hardware components, and they have been developing software to run all of this in a very efficient way. We decided to enable our customers to do the same thing because not everybody has an army of engineers like Google and Facebook have. Very briefly, Excelero NVMesh Server SAN. What is it? The shortest explanation I can give you is it's a software-defined block storage solution. So we use standard servers with state-of-the-art NVMe devices. We are distributed NVMe, or we provide distributed NVMe. Essentially, we enable companies to pool NVMe over the network and use all NVMe benefits as if it were used locally. Josh is going to tell you much more about that. We're scale-out server SAN, so we scale data center-wise. You start with just a few servers and you can scale over multiple racks. And we allow converged and disaggregated architectures, very important for the flexibility requirements that customers have today. So they can perfectly start with an NVMesh environment with what we call a zero-U concept, use application servers, put some NVMe drives in there, create a scale-out block storage environment. But if they feel the need at some point to add much more capacity without adding a lot of servers, they can add a few boxes that are just filled up with NVMe as well. So a lot of flexibility on that scale. That is the last slide I will be talking to. Very high level, the simplest explanation of our architecture. You have a number of standard servers with NVMe drives in there, and you put NVMesh software on top of that. What NVMesh is going to do, it's going to abstract all the capacity of the NVMe drives in your server and create one pool of very fast block storage. Okay? The software enables you to provision block volumes, and Josh will be talking about that more in more detail. And those block volumes can be either accessed by applications directly or through file systems. For example, we support GPFS for very large clustered file system environments. I think that is all I needed to cover. Josh, I think it's over to you.
Right, thanks. So first off, everything you're seeing here is not embargoed. We're not presenting anything that's embargoed today. And you're welcome to take pictures, but you're also welcome to get the complete presentation. So be very happy to make that available. Either you have my contact information.
We are going to make it available.
Okay, so you're, again, welcome to take pictures, but we'll get you the slides in short order.
System instantly.
That's true.
Okay.
Lastly, the reason for that is not that we don't want to show you things that are new and cool, is that we have a philosophy that we show you what's real. With that, we only came out of stealth in March. However, we came out of stealth at version 1.1 with customers. It's very important to us. So the things you're going to see here and we're going to talk about, they're available right now. You can try the software literally after this demonstration if you want to. Lastly, the demos we do at Tech Field Day were live, and the demo that we're going to do today will be live. So I'm going to preface it with that because that way, if it crashes and burns, I have the excuse that we're doing a live demo. It's not a video. So Throwback Thursday, this is a reference to that event in March. We went ahead and we came out finally. It was our kind of coming out party. And a lot of it was focused around performance. We didn't necessarily intend that. We always talk about performance because we're optimized for NVMe. And NVMe is a very high performance media. We completely unleash the performance of that media and allow you to get every bit of IOP, every bit of capacity, every bit of throughput at the low latency that NVMe provides. So our product, though, is not necessarily about high performance. It's about low overhead. It's about not putting a tax on top of what you paid for. Standardized servers, standardized media, put a software layer on top, and extract every bit of performance that NVMe gets you. So that's how it comes across as performance. But what we realized is...
Josh, is that
yes.
Tech Field in this picture?
Yes. This was the actual room we did.
Was that not the last one, the one before that would have been in March?
Number 12.
Yep.
12.
It was storage Tech Field Day.
Yeah.
Is that
Hoskins.
Clever, attractive looking gentleman with a white shirt. Our table, someone we know.
Yeah.
Yes. Yeah.
No, that's Rob, that looks like Rob Novak.
We had some tough players in the room. It was a good.
Oh no, it's Howard, isn't it?
Yeah, it is Howard. Yeah.
he's the handsome one.
So the key is a lot of performance messaging, but really what it's about is giving you flexible functionality, efficiency, getting what you paid for, lowering overall cost, and really letting you get operationally efficient. So we're going to use a good old car analogy. My colleague here picked these cars. I would have picked Maseratis. I like the Italian cars, but since it's storage and we want reliability, we went with something German
Ask Chris
instead.
what he drives.
What do you drive?
You.
No, you. We want to know.
Is it the one on the left or the one on the right?
So with that, of course, you have Porsche two-seater Carrera of some type. Very, very fast. Not the most practical, but you can also get a Panamera. And you're going to fit 4 people with their luggage. You have different gasoline or diesel options. 4-wheel drive is available. You have a lot here, but it's still an extremely fast vehicle, yet it kind of melds the two together. You get a lot of functionality, a lot of utility out of it. And that's really the apt analogy for what NVMesh is. It gives you the performance of a high-performance car, but it gives you the functionality you need and the efficiency you need to operate in your environment. So there was recently a study that came out, a survey from ESG. I know we don't like to mention other, but
We don't care.
Came out outside. We don't care. Came out from ESG, and they asked basically, what do you care about from your storage vendors today? And these were some of the answers. We've extracted some of the ones, which is it needs to reduce operational cost. Get the best performance you can get. Maybe it's the best performance per dollar, but it's best performance. They want a flexible hardware infrastructure. That is, if at all possible, avoid proprietary hardware. Avoid this model where you overcharge me for something that I can buy, commodity. And have a compelling vision, which we believe we have a compelling vision. Integrated into the computing stack. And that's really what we're focusing on. A question that may come up later, you might ask is, do you guys integrate with VMware? The answer is no. We don't have any plans to integrate with VMware. The reason for that is, and we use the analogy of hockey in the US, or Canada probably, that we like to skate to where the puck is going, not to where the puck has been. So with that, we're focusing today on container environments. We also work with OpenStack. So if you want to do modern compute, you want to adopt the methodologies of these big five that we touched on. But that's what we're focusing on, these kind of environments. And reduce capital costs. How better to reduce capital costs than to allow you to pick the servers, the media that works for you, you control that, you put a software layer on, and you get better performance than anything you can buy in the market today. So our focus areas, you see at the top, efficiency. We want you to be able to utilize all the capacity that you purchase. We want you to get the best, extract all the performance that you pay for, extract all the capacity, get an entire pool, and bring up the utilization rates that you normally see with flash. They can be as low as 25%. With us, you can get as arbitrarily close to 100% capacity utilization as you're comfortable with. If you want protection, then today with RAID 1 or RAID 10, you can get arbitrarily close to 50%. But we've had multiple customers that say that they're only at 25, 15, 35% utilization because they have these individual pools and each one on average is underutilized. Flexibility, you get the ultimate flexibility. We can deploy in what looks like an all-flash array, build your own, or we can deploy by simply putting 1 or 2 NVMe drives per server over a very large number of servers. So you have the ultimate amount of flexibility. Performance, I've touched on it. Yes, question?
Flexibility, will it also accept non-Excelero logical volumes? Will it work with other vendors?
Yes. That jumps forward a bit, so we'll jump forward and we'll come back. We are a software layer on the client that enables access to our block device. However, it is completely compatible with any other block clients, with any other block devices. It shows up as its own set of block devices. So you could even mix this into a fiber channel system as long as it had an Ethernet NIC that supports our technology. You could even use NVMe over Fabric simultaneously while you use our solution. Additionally, just as an adjunct to that, if you wanted to, you could even use SAS and SATA. We downplay this because we're optimized for NVMe, and that's where you get the best benefit. However, you could use SAS and SATA drives and NVMe over Fabric targets when they exist. I don't mean the open source software, I mean hardware targets. So we are future-proof and fully integrated into these environments. Scalability. There is no one in the market that is as scalable as we are for any kind of NVMe over Fabric product, basically any kind of product. We are the world's most scalable local flash performance solution that's out there. We can literally go to, I think it's 50 petabytes of storage if you wanted to, with the product today. You could go to, and this is why we don't talk about performance. I could wow you. We could scale to hundreds of millions of IOPS. But what are you going to do with them? It doesn't matter. The point is we're scalable. We'll let you scale to very large capacities and get every bit of what you pay for, however large you scale. And ease of use. You'll see some demonstrations. Ease of use, both we have a GUI, we have a RESTful interface, and with what we're going to demonstrate through Kubernetes, you'll see that you can completely provision and attach our storage in a container environment without any administrator doing anything with the storage. It just happens automatically. So how do we meet these requirements? And these mimic what was on the other slide, or mirror. Efficiency, I told you a bit about this. Very high utilization rates for NVMe, standard hardware, and more importantly, no CPU overhead. You may have heard me say we're software-defined storage, and I told you you could put 1 or 2 drives per server. You can use those servers for compute, because in our software, unlike any other product on the market today, when we are sharing and utilizing drives and sharing them to other hosts, and other hosts are consuming IOPS or bandwidth, We do not tax the CPU of the host that's serving that. And we call this true convergence. This means is if you want to actually have one cluster and not have an external array, everyone can participate in the cluster as both a client and a target, but the targets are not paying that usual noisy neighbor penalty. And we'll go into this in more depth later. Scalability, I touched on that, so I won't touch on that again. Ease of use, we're very easy to use. You'll see that in just a moment. Flexibility, we ended up talking about this, about how flexible we are. And performance, it's a given. The media is highly performant, so we're highly performant on top of that. So what can you do with this? Basically, we're seeing use cases in all these different applications and verticals. Now, the fact of the matter is, we are highly performant. So you may be tempted to say, well, not everybody needs that performance, and you're right. The key is almost every vertical, almost every part of an enterprise even, has some section where they do need that level of performance. If they didn't, why would people be putting flash locally into servers? If they didn't need the performance, they wouldn't be doing it. When you put flash inside a server, it gives you a local pool. We're back to DAS, direct attached storage. This is a concept that was popular in, the 90s? So if you put flash into a server, there's got to be a reason to do it. So people do want that performance. What they don't want is the individual pools. They don't want to lose their data. They don't want to have to replicate outside. In other words, they want to do things like they used to, but get all the benefit of modern media.
Can I jump in for 1
Yeah.
second? Because you're not seeing the online conversations on
Oh.
Twitter. This is a very important slide. Today we're talking about containers. What I may not have made very clear today is containers is just one use case. And the point of the session is to show you how our technology is used for a specific use case. It's important to see that all of those applications can be run on our technology. So if containers, for some miraculous way, don't become the massive thing that we all think it's gonna be, no problem for us. There's a lot of other applications, like for example, database as a service, which Josh is gonna talk about later on as well, which is also a great application for us. Sorry for that.
Oh, no problem. That's actually a key thing. And I forget, it's actually my fault, my apologies that I have not talked with all of you before. You're not that familiar with our product. Containers to date, this is a new functionality for us, added on to the base functionality we already have. It's really just an automation into a layer that lets you run that. And as Tom said, if you don't want to run containers, that's fine. The product works as is in all these traditional environments. So we're a fan of IBM Spectrum Scale, and you'll learn why later. Genomics, risk analysis, analytics, as well as risk analysis is used in HPC. We're in burst buffer and seismic modeling, as well as visualization. Machine learning and predictive analytics in IoT. Transcoding for media and entertainment, as well as actually post-production. We have a customer entering POC very soon who doing 4K workflows is really thinking this is going to be the ticket for them for post-production. Database as a service and microservices. So all these things are available. And again, we'll make these slides available to you so you can have a reference for this. And because we're going to make these slides available, and I don't want to run too short on time, I'm not going to spend too much on this. I will tell you that we have focused on hyperscale web and cloud. That has been our main focus. That is why you see representatives from LinkedIn, for instance, who gave a presentation at our event in March when we launched. We're also part of Open19. If you don't know what that is, it's an initiative by LinkedIn. They cannot say this, but we can. Open19 is basically the Open Compute Project, OCP, done right. So we are the storage layer, the first and only right now storage product, block storage product that's part of this Open19 project. So web and cloud, they need the ultimate scalability. They're already using local flash. What they like to get is better efficiency, and that's our story here for web and cloud. You can use it in web and cloud for, again, well, we're talking about Kubernetes, MongoDB, but even if you do bare metal provisioning, we can use it for Postgres, you can use it for Cassandra, you can use it for Apache Spark. The list goes on and on. Any application that can benefit from a high transactional efficiency load, so that is low latency because you have a high transactional rate, can benefit from this product. Innovative enterprise, what we mean by that is what I touched on earlier. Every enterprise has got a small section that's doing something. For example, we have Axel here, who is one of our representatives in Europe, who's been working with a particular bank in Europe, and they are doing basically an analytics run on data that used to take them 40 hours to do a report that they had to run every 24 hours. You can imagine that was kind of a problem. This is for compliance. So I think that run is down to 4 hours or 5? 6. 6? Okay, my marketing side came out, I exaggerated. From 40 hours to 6, so this well fits within the window. But it's not just that they're getting that performance, they've reduced it, they're getting it with redundancy. They're getting it with resilience. They can have a server fail, they can have a drive fail, and it keeps going. That's the key thing. This is something for compliance they have to do every day, and now they have the confidence that they can go ahead and do that. So real-time analytics, again, big databases. Some of these overlap with others, but very, very high transactional loads in enterprise. High-performance computing, I think that's obvious. High-performance computing needs very high performance. The difference is oftentimes they use things that require very high bandwidth. Now, NVMe drives also offer very high bandwidth. The question is, how do you take a whole bunch of NVMe drives? How do you take hundreds or thousands of drives and unify them to be able to use them for one purpose? We can be the answer to that, which is get you very, very high throughput. We'll touch later on a use case. NASA Ames was one of our first customers in California, and they're currently using a completely shared CXFS file system amongst 128 nodes, and on a regular basis getting 140 gigabytes per second of bandwidth and some 30 million IOPS. Drifting towards performance again. My key is not to tell you that, well, these numbers are so huge. They're getting the aggregate performance of the devices that they paid for. The difference is they unify it and they put it behind one file system. And rather than slicing up their data sets into 128 different pieces, there are 128 nodes in the cluster. Rather than slicing their data up, they just put all the data on one file system, and every host accesses that data as if it's using local flash. Database as a service, key thing here. Let's talk about Cassandra for a moment. Cassandra, in-memory database. Why am I talking to you saying use us, use Flash for an in-memory database? Well, the key thing is any in-memory database, best practice is to go ahead and put Flash on that local server. It's doing replication. We're not going to do any data protection here. We're going to do RAID 0 volumes. The database itself, or their shared nothing architectures, they're going to replicate 3 times or however many they do. So again, why are we saying that you're going to add us a centralized resource into a shared nothing infrastructure? The reason is that the best practice is to use Flash because these databases, if they go down, they have to dump the contents of memory to a Flash device. You need that as fast as possible. When they come up, they need to load the contents of memory from a Flash device. But moreover, when they fail, if you have a 2 terabyte in-memory database, when one node fails and a new node starts up, it doesn't have any data on that local flash. It's going to transfer 2 terabytes of data over the network, which is going to impose a huge penalty on your network. It's going to slow down your existing systems. If you use NVMesh here, you can use shared devices, and you can, when one node fails, a physical node fails, another physical node can take over. It can use the same logical device, and then it only replays the transactions for the time that that third server has been offline. Meaning you may only transfer megabytes of data rather than terabytes. So this is what you get for operational efficiency. Additionally, if you need large devices, you can pool multiple devices together. You don't have to buy a 3 terabyte drive for every single host. When maybe one host needs 1 terabyte and another host needs 2, you can buy exactly the storage you need and use logical volumes to assign exactly the sizes you need. And containers, we're going to go ahead and go into that, so I'll skip this one here. Any questions so far?
So just on that last point,
Yep.
do you think that people are starting to realise that replicating data, large volumes of data like that, at an application layer is possibly not the most attractive way to do things?
That's a tricky question because it's kind of like religion. So, and this is my opinion. My opinion, the answer is not necessarily. I think people are going to say that shared nothing architectures and replicating at the application layer is correct for some applications. So, but there are ways you can improve efficiency, as I mentioned, that even when you're replicating, sometimes going to be a very big penalty to recover when there is a failure in one of those replication schemes, and we can speed that up immensely. Could you also eliminate some of that replication? It's possible. It's absolutely possible. If folks want to do that, they can. I think shared nothing architectures came in to solve a problem, which is to use standardized servers and not require redundant storage. And we play into that in that we fully support standardized servers. You could replicate with us, or you could use us as RAID 0. That's actually part of our flexibility, that we're not going to force you and put an additional replication tax. So did I dance around that enough, or give you an answer that makes
what
sense?
you're saying is it depends on your requirements. I mean, if you have a server that never fails and doesn't fail for 6 months,
Yep.
you know, that one recovery you do in 6 months where you copy 2 terabytes of data, you might say, who cares?
Exactly.
But if you're
Yeah.
if you're in an environment where that happens once or twice a day, you'd probably be going, well, maybe we architected this wrongly, or we bought the wrong service or something. You know, but,
Absolutely.
yeah.
Yes, you can increase reliability or choose not to. You're absolutely right. What we're also trying to do, to be clear, is ignoring containers. Just simply, there are a lot of traditional applications out there that are high transactional loads that enterprises or non-enterprises find it very difficult to move into the new paradigm. What they'd really like is, I just want to use a block device like I'm used to, but I want the performance of local flash. But I also want centralized administration, data protection, the ability for a host to fail, the ability for a drive to fail. And so far, these two things are at odds. They didn't exist. But with Excelero NVMesh, they do exist. So it gives you a little bit more time. You can move your applications over. They're block devices. Put any file system you like on top if you need a file system, and you're off to the races. You get the performance of local flash, all the flexibility you're used to of centralized storage. So it's the best of both worlds. All right, so containers. Our objectives were, we want to allow for transactional containers. That is, there's kind of been a dearth of people putting really high transactional loads, transactional to the storage, that is, on containers. Because if they really needed the performance of local flash, they were tied to a node. So we wanted to give containers persistence, but local flash performance, with the ability, of course, to be able to move that container elsewhere. And that's that freedom to move amongst physical nodes. We needed consistent storage, that is, consistent storage performance. If a container was on one host and then it moved to another, or I spun up more containers, no matter what physical node they run on, they need to have the same kind of access. In other words, I want to eliminate data locality. Sometimes I get asked, do you guys do data locality? I go, yeah, it's local everywhere. It's hard to believe, but it's anything that's on our storage to any particular host, wherever it is, it performs just like it's local flash. Therefore, there is no need for data locality because it all acts like it's local. Abstraction of logical volumes. That is, you need to break this. Like I have a 3 terabyte drive, which means I'm limited to 3 terabytes on one host. No, we take all the storage, we pool it together, and when you allocate storage from us, we use pieces of drives. You don't have to allocate even an entire drive. We use segment allocations per drive. Adhere to the container philosophy. That is, use standardized hardware. It makes me nervous when people take pictures. Use standardized hardware. Don't tie me down to an appliance. If I want rack level flash, don't make me put a specialized appliance in the rack. I want to build my own. So we support all standard servers. The 0U concept, I touched on this earlier. Why is it 0U? If you go fully converged and you put NVMe flash in each node, you're adding a virtual all-flash array. But it's not taking any space, it's 0U. And it performs better than any all-flash array on the market. It will not hit the CPU on the targets, which means, and we call this logical disaggregation. We logically disaggregate the media from the hosts, allowing you to use it, but not impact the CPU on those targets. And lastly, data protection and availability. You had to be able to have a node fail and you had to be able to have a drive fail or some combination of those, and yet keep the data available and, of course, protected. So what does it look like? You just run your container nodes the way you normally would. This one's showing Kubernetes. We are a plugin. Currently, we're a flex volume plugin into Kubernetes, which means you can take your existing Kubernetes environment, add our plugin, and you can get these benefits and use NVMesh storage. So overall, what's our architecture? Now, this is our generalized architecture, not about containers, our generalized architecture. I was told you guys want technical details, and you're going to grill me. So this is the time. I know we had the lunch stuff, and everybody knows. This is the time to get into this. Ask me what you want. You've got this opportunity now. So server SAN, we're 100% software. Bring your own hardware. Unified NVMe. We take all the NVMe and pool it, whether or not you do dense nodes or you do nodes that are sparsely populated. All of it becomes one pool, and you carve out logical volumes however you want. No CPU on the targets. I talked about that already. Very flexible and 100% efficiency. That is, if you put in enough networking, we will extract all the IOPS and all the bandwidth of the drives that you provide. So you'll get 100% utilization out of them, rather than being trapped. What I mean by that is if you can put 6 NVMe drives in a host, some of these drives, that may give you 3 million IOPS. How do you consume that in one host? It's near impossible. But by offering it up on the network and allowing multiple hosts to share that in a SAN methodology, you can extract everything that you paid for.
So just can you run through what enables you to beat local latencies over the network, even assuming the fabric mesh would...
Did you say meet or beat?
Exceed. So
we don't exceed.
yeah.
We can't do any better than the... Yes, I will answer your question. We're heading into that right now. So this is an overview of our components. As mentioned earlier, we do have a block driver that's installed on clients. And this offers up what looks like, when you attach a logical volume, it looks like a regular Linux block device. It appears under /dev/NVMesh as a name that you give it. It just looks like a block device, acts like a block device, walks and talks and quacks like a duck. It's a duck. Management. We have a scalable management layer. You need, at minimum, one host to run our management. Management can run on some of the same nodes that you're converged, or you can run it separately. And if you want to see, you don't want me in the picture?
Yeah, I did run
That's true. I agree. My wife says the same thing. Just one is enough. One of me is enough. You can scale management for redundancy and for scalability. So one is minimum, but you can scale it up. We use MongoDB in the background of this. MongoDB supports a replicated scalability. So our database and our management is scalable as well. The third piece of the puzzle is a target. There is software that runs on target systems. For us, target systems are those that have NVMe drives. So we run some software there that enables to do this magic. But I'll explain what that magic is and why, even though we're running software, why it doesn't use any CPU.
Where does the run? Is it hypervisor level or is it OS level?
So it's OS level. On bare metal systems, actually anywhere, these two are kernel modules. The client and the target are Linux kernel modules, basically any distribution of Linux. We haven't found one we can't use yet. Officially, we like to support CentOS and Red Hat, although in Europe we also support SUSE. So those are kind of preferred, but we also have customers running Ubuntu and all sorts of various versions. But we haven't found a Linux yet we can't work with. So I'll explain this in just a moment. So that's just basically the three components. We have a client, we have a target, and we have management. So centralized management, what does it do? It's a Node.js application sitting on top of MongoDB. It provides a complete RESTful interface, and we built our GUI entirely on top of our own RESTful interface. Therefore, anything you can do in the GUI and more, you can do in the RESTful interface. For modern infrastructure, it makes it very pluggable. The centralized management is really a configuration master database. So clients and targets report into the management, basically their inventory. Clients say, I'm a client, and I have this NIC. And targets say, I'm a target. I might be a client too. And I have these NVMe drives, and I have these NICs. By the way, we can support up to 8 NICs, and you can aggregate the performance of that. So that means you can get up to, with today's NICs, 800 gigabits of bandwidth. If that's not good enough for you, please see me after and we'll come up with something more. And it transforms all the drives into a pool. Basically, it takes all these inventories and says, this is the pool. And then you create logical volumes from that. When you create logical volumes in management, all you're doing is you're creating a definition. You're just saying, hey, give me a RAID 10 volume that is striped 8 nodes wide, and it's a RAID 10, so it's also mirrored. And you go pick the right drives and whatnot for me. And it picks it and it makes a definition, and all I have is a layout of a logical volume. Nothing's happened beyond that. It's very scalable, which I talked about. You can build management also as scale out. RESTful, I talked about. Easy provisioning and flexibility with some policy tools. We allow for policy management, insider management. That is, you can have a rack and row awareness. So for example, if you have 2 racks next to each other and you want to create RAID 10 or RAID 1 mirrors, you can define, make sure when you create these logical volumes, pick drives out of one rack and pick some drives out of the other rack for the other half of the mirror. That way you can actually have an entire rack fail and you stay up. You can do this on a rack basis, a row basis. You basically make these policies up however you want. The client is an intelligent block driver. So what it does is, if you remember, I said a volume gets defined in the management. It's just an entry in the database. Very simply, a RAID 1 volume would say, use this part of this disk on this host, and use this part of this other drive on this other host. That's a volume. Maybe if we...
granularity going to, Josh?
It has to be a minimum of a gigabyte for the logical volume, but other than that,
But
no.
within that, how much of each drive are you carving up into making a logical volume?
As much or as little as you want.
Yeah, but are you doing it by chunking it, or are you just saying, here's a section of it?
So all of our allocation is done by segment allocation. So we look at the inventory of a given drive. If it's a 400 gig drive, and we also support the drives either in 512 or 4K native formats. We'll ignore that part for now. Let's say a drive has sectors 1 through 10, and this other drive has sectors 1 through 20. If you were to allocate a 4-sector long RAID 1 volume, it will simply take 4 contiguous sectors from one drive and 4 contiguous from the other, even though they were not the same size, and we'll mirror those.
Yeah, so that the implication of that is that if you were creating and destroying lots of volumes of different sizes, you would eventually fragment your storage. So does that mean you could end up with a volume that consists of many parts of many?
Yes, you
devices?
absolutely could. However, from a performance point of view, the media won't care. When we do our testing, we only test with random loads because, remember, since we're talking about flash drives, they already, at the FTL layer, they're not really presenting things in contiguous order. They're just giving you a virtualized table.
But
that's
do you have
contiguous.
any maintenance that optimize over time, low periods and things like
Not-
that?
Fragmentation tools.
Not in this version. So I told you earlier I'm going to present everything that's real today, and that is, in what we have today, we are thick provisioned. We're using these sizes,
And you're using variations of RAID today. You're not using erasure coding or.
today we're only using RAID 1 and RAID 10. There are actually reasons for that of why it's actually less costly. If you have a high write load, it's less costly to stick with RAID 1 or RAID 10 than it is to go with an erasure coding scheme when you consider how you're going to wear out the media. However, that said, by the end of the year, we can talk about this anyway, it's not really embargoed. By the end of the year, we will have a RAID 6 scheme that goes over at least 4 hosts and allows for the failure of 2 nodes and brings down that overhead for data protection significantly. So we will introduce that. As well as just a future-looking statement, virtualized blocks are also on the roadmap. Have a couple of beers, we'll tell you when. But
No.
virtualized blocks are on the roadmap, so we will deal with these kind of issues. But basically, we had to start somewhere, and we've started where we are to give you, and that's also why that's kind of focused on performance.
So how many disks, say, or chunks on various disks will you support contiguously? Could you have, say,
You can
8
split
different disks or more? Or?
a single volume can spread over as many as 128 nodes.
Yeah.
Each node can have today up to 24 drives. So if anybody wants to do the math, 24 times 128 is the maximum number you could split over for a single volume. It's a QA limit, nothing more, so we could go to more drives per host, but it starts to make less sense because even at 24 drives, you're oversubscribed on that server. You can't get the performance out of those drives. You run out of PCIe lanes. It has nothing to do with us. Did I answer those questions there? Okay. So the client driver completely understands the layout of volumes, and that's how we're so scalable. The client driver itself is what performs the I/O in a RAID 1 mirror. It sends the data off to one host and to the other host, and it does not act the write until it's completed. Nowhere in our system do we do any caching. Everything is asynchronous, atomic type operation. We do storage with ACID operations. So there's no caching here. Some of our performance, some people get their performance through caching. We don't get our performance through caching. Everything is synchronous. Everything's about data integrity. Ubiquitous access. So the client, yes.
Wouldn't adding cache improve performance even further?
Sure, it might.
Why don't you do it?
We might, but when we already got to a point where folks said you demonstrated 4.5 million IOPS in a live demo at our last presentation. Who needs that? How many more?
I just met people that need 6 to 8 million IOPS.
Million or billion? Million.
In the HPC.
I can give you 10 million IOPS in 2 servers today. It's very again. I'm not trying to be flippant. I'm just trying to tell you that if you can aggregate all the NVMe and give the right amount of network bandwidth, we'll get to any number of IOPS you want. I have a customer right now that's testing us in our lab that insists they need 20 gigabytes per second writing 24 hours a day, and we're meeting that. It's just a matter of how the hardware is more the problem than the software.
But Josh, if you cached caching would cause you a problem because when you've got many nodes and you're doing write caching, all of those other nodes would have to know about that.
Exactly, and that's part of the complication. However, as Tom mentioned, some of our patents that are filed but not yet granted actually are directly looking into that.
Do you partner with Intel to use their cache algorithms protocols? Because they've got very good ones with CPUs.
We do partner with Intel. However, we're not doing what you say because remember, we're not using any CPU.
No, but their protocols for CPU cache invalidation and tracking,
Yes.
and snooping is incredibly effective.
So I could do that on the client. I can't on the target because on the target, our data path does not go through the CPU.
No, I'm not talking about going through the CPU. I'm talking about using the cache protocols that CPU manufacturers use to manage their snooping. If you could use that, you could have very effective.
I could, but normally I'd have to do a lot of this on the target. To use those protocols, I have to run a process, which means I have to context switch.
You have a directory service. Intel's running a directory service on their CPUs to do this.
But each time I go in and out of the CPU, I incur as much as a 5 microsecond hit.
No, but I'm not talking about doing it on the CPU. I'm talking about you having a directory service to cache your data distribution, for example. So you could do things like Intel's doing with its high core count CPUs very effectively.
I agree with you on the client side, and we'll get to the reason why.
We'll have it over beers, but there's some very interesting things with their new cache structure.
So we're going to have to pick this one up now. The target module, I'll explain. So this will start to make a little more sense. The target module basically takes an inventory of the NVMe drives, reports it to management, and then it sits there. When a client says, I want to use a given target's drives, the target module looks at the client, looks at the definition, looks at the volume definition, makes sure that they match, and then it goes ahead and it makes an RDMA connection, a remote direct memory access connection, between the client and the target drives, directly to the drives in the host's memory. Once that is established, the target is not in the data path. So even we call it a target for storage folks to understand its functionality. However, unlike other software storage targets, we're not actually performing the I/O. A client actually goes across the network to the remote NIC once this connection is set up, and then the NIC does a PCIe, peer-to-peer transfer, directly to the NVMe drives. And then the response goes back directly to the NIC. We don't even send an interrupt to the CPU. This is why we can't take advantage on the target side of anything that you would normally associate with Intel acceleration for storage on the target, because we're not running in a core. The CPU doesn't even know an I/O has occurred. We're using the memory controller only and PCIe peer-to-peer communications directly on the PCIe bus. So what we've done in a way is we've extended the PCIe bus from the client over a network all the way through to the target directly to the drive. This is how we can perform millions of random or sequential IOPS on a target host and not use any CPU. Lastly, there's something called the Topology Manager. It's part of the target. This is what coordinates between all these systems and watches for errors, watches for things that go wrong, that is changes to the network topology, disks failing, disks being removed, disks added. That's part of our target. Now this is when we will use a little bit of CPU. Drive failures and rebuilds are handled by the Topology Manager. They're not handled by the clients. This is so that we have complete control over this. The Topology Manager also is what clears stale locks. So for example, you had a client that locked a given range of blocks. It was going to do an operation, and then that client got struck by lightning, and it left the locks. The Topology Manager watches for stale locks, and then we go ahead and clear those locks. That's the kind of operations that Topology Manager does. Data protection. We touched on this. Today we support RAID 0, concatenated volumes, RAID 1, and RAID 10 volumes. As I mentioned, erasure coding will be coming, but this is what we have today. We do support target-side locking. There's been those who said that you can't share NVMe over Fabric. That's true. NVMe over Fabric, as the spec is defined today, you can't share one drive amongst multiple hosts. You can if you do namespaces, but you can't share one namespace, for instance, among multiple hosts. Our product has been set with RDMA atomics, allowing multiple clients to use this from day one. And with drive failure scenarios, we handle automatically drive failures, drive replacement. You can add new drives or hosts at any time. NIC failures, NIC recovery, everything is done in the product.
Well, that RDMA locking then,
Yes.
how hard was that to develop? Is that a fairly unique bit of IP for you, or is that a fairly standard approach?
Applying the RDMA locking to storage is what's unique IP for us. However, atomic RDMA locks have been part of what's known as MPI in HPC since basically the development of InfiniBand. Locking, you can imagine, since RDMA is actually letting one client manipulate memory on a remote host, it was very important from the get-go that a client manipulating memory on a target doesn't manipulate memory it shouldn't and can lock certain regions. So locking in memory has been a part of RDMA since the beginning. Using it like we are for storage, that's what's unique. Scale, I told you we're architected for scale. I covered some of this as well. You will have the slides. And vision, I actually already told you a little bit about the vision. We are where we are today. However, we'll be adding things like a more advanced erasure coding, which gives you lower overhead, keeping the performance. We're going to allow you to mix these things as well, because adding erasure coding is going to add latency. So you'll be able to have some pools that are erasure coded and some that are still at RAID 0 or RAID 10.
How do you tie in your array of data services you need? Compression, dedupe, all of that, where would that fit into here?
So those are roadmap items. I'm not prepared to talk about them today, but if you're having trouble sleeping, do Google searches for our patents. You'll find one on a distributed metadata mechanism that actually can allow for a dedupe, for instance, to have a single shared pool of storage where the processing is done on the clients, yet you can actually have, even though there's individual clients, you can do a single shared dedupe pool. That's through a distributed metadata mechanism that is one of the patent applications, and it is a roadmap item. So it is possible, and we'll be very excited to tell you about that when that comes out. Okay, demo. I want to make sure we get into this. So we talked about containers. On top of this, that you should get local flash performance, mobility of containers, deterministic performance, abstraction of logical volumes away from physical media, use only standardized hardware with no noisy neighbors, and allow for physical drive or node failure So let's go ahead and show you some of that. The layout of the demo is we have 4 nodes. How many people here are familiar with Kubernetes? Wow, okay. That's great. So we have 4 nodes. One is the Kubernetes master. This is just a switch. The other 3 nodes are running as Kubernetes compute nodes or Docker container nodes. We could run jobs on here, but I've chosen not to. I've restricted so that we're not running any jobs on here because I'm also running the NVMesh management on here. And part of the demo, I kill containers by killing the hosts, and I don't want to take out my management today. So there's no jobs will run here, but they can run on these 3 nodes. So 4 physical nodes. Each node has 2 NVMe drives, and they're split a bit. On some of the nodes, I have them split so I can use one drive locally, and I have the other drive allocated to NVMesh so they can be used for shared volumes. So let's go ahead and get into the demo. Where are we on time?
We are just
Don't
about
worry
good.
about time, I'll make sure that you don't go over.
You're not going to get the extra.
That wasn't the part I was worried about.
I wouldn't underestimate him.
Yeah. We need to be done at 10:03.
Yeah, if you take your half hour for the demo right now, you have 5 minutes for the myth busting.
Okay.
Myth busting.
That's good.
You need a sand timer.
All right, so this is a cluster that's actually running in the United States. I'm going to go ahead and log in to our administrative interface for this cluster, if I can even type. And here you can see our GUI. We've got some nodes that say they've got a couple of alarms, which I'll explain in a moment. Graphing, this is all very standard. There's options down the side here. Overall, what's the health of the volumes? What's the health of the targets? What's the health of the clients? How all your capacity is allocated, and some of the volumes that we have here. If I go ahead and show the clients, I said I'm in converged mode. So I have 4 servers, but each server is both a client and a target. So they're going to show up on both lists. Here's the client functionality. On the volumes, you can see I have 2 volumes. In fact, I don't want this one. So I went ahead and deleted that volume. I've got this NVMesh volume. This one I'm going to leave created. This was automatically provisioned originally by Kubernetes. However, part of this demo is to do a performance where I needed a very large file, a 256 gigabyte file. It takes about 10 minutes to create. I didn't think you want to sit through that. So I'm not destroying that volume, but I will show you how Kubernetes can automatically create new volumes. And on the targets, you see that I have the same list of targets. Now, these are in an alert mode, and I'll tell you why. It has to do with, we normally take over any NVMe drives in the system. So here you can see, I see 2 NVMe drives on this node 22, but I want to allow the demo, for part of the demo, I want to use a local drive, local to the host, so I'm going to evict it. It's making me give the password because this is, are you really sure you want to do that? Now the disk is evicted, but we've gone into an alarm mode. So if I go back to the dashboard, you see I now have 3 systems in alarm because it says, well, wait a minute, this disk is in a funny state. Normally you'd use eviction for forcing a drive to fail, essentially. Maybe you wanted to replace a drive. Or simply, like I'm doing here, I had some drives that are physically in the systems, but I want to make sure I don't use them for anything right now. I can also do this with my provisioning groups, but maybe I haven't set up provisioning groups yet. Long story short, I want to assure you that those alerts are intentional. And here's from ones I just got from the operation I did. I'm going to act those. But that gets to show you a little bit about how easy it is to do things on the system and work with the GUI. Now I'm going to remind myself here of what we're doing. So on Kubernetes, let's go ahead and show the nodes. So can you guys see that window? Maybe make it a little.
You're good, I think.
So I'm just going to show my nodes. This is as I told you about. I have 4 nodes. 21 is our master, which I'm not scheduling on. 22, 23, and 24 are there. Let's go ahead and look at some of these files. So if you look here, I have various YAML files, the definition files used by Kubernetes to define pods, replication controllers, that kind of thing. I'm going to go ahead and look at my Mongo one. Because I've chosen MongoDB, not for any love of MongoDB, it's simply I had to choose a database, I chose MongoDB. This is a definition of a replication controller. That is, I want a Mongo pod to run, and I want Kubernetes to automatically keep one of those running all the time. That is, if it dies, I want Kubernetes to start up another one. So a very simple definition. I don't want to give you a tutorial on Kubernetes, so we won't go through there. The important part of this file is to know that here is the definition of our Flex Volume plugin. This can be added to Kubernetes after the fact. We're saying that it's an Excelero NVMesh driver. Make your file system type XFS. It tells where our management host is. And the volume, this is the volume name, NVMesh volume. If you notice, NVMesh volume matches the volume that is on here, NVMesh volume, because it was created by Kubernetes. And that's what's going to be used. Okay, so get out of that file. Let's go ahead and show these local drives. I told you that 3 of the nodes, or actually all the nodes, have local drives. On each one, I have mounted one of those SSDs under /mnt/local SSD. Kubernetes only uses file systems. It can't use a raw device. So it only uses file systems, so I've made these file systems available. They can be passed through to Kubernetes as a volume that they can go ahead and use locally, local flash. So that's basically the setup of what we have there. If you look at the file for this, it looks very similar. This is the replication controller defined to use local storage. So instead of a flex volume, it would just use a local disk down here. Any questions about the setup so far? I hope not, because I need to get going. I showed you the GUI, so we talked about, I logged in, we showed clients, targets, and I explained how OneDrive is being used, so we've cleared that alert. So let's go ahead and do some demonstration with Kubernetes. I'm going to go ahead and start up a replication controller for local storage. So there, I've created that replication controller. If I show the pods that are running, there's only one pod running. It happened to go onto node 23. So let's go ahead and get into that pod. I'm now on pod 23. If I do a df, I can see that I have this /data/db mounted on that local flash device. This is simply to tell you that, hey, this stuff works. This is, by the way, none of this is NVMesh yet, to be clear. I'm just trying to show you that this is what you would do with Kubernetes. If you wanted local flash performance, this is what you'd have to do, is set up local drives. So I'm going to go into a directory that I already have on each of these local drives that has some FIO runs. And we're going to run on this system a couple of different tests. Now this takes 2 minutes. So now I get the soapbox for a little while. This test is just to show you the performance of local drives. There's nothing unique here to us, again. I'm just showing you this is using local SSDs. But the question that comes up is, why aren't people doing this? If you get you're going to see really great performance. Why aren't they doing it? Because it's a local drive. It's tied to that one host. If and when this container has to move to a different host because there's a problem, it doesn't take the data with it. You're forced to do something else. The only way you can go ahead and have data protection is to go ahead and do replication, which imposes the whole overhead. What I want to do is I want the freedom to be able to deploy a MongoDB or a Postgres or an Oracle database, any of these things. I want to use storage as if it's local and not worry about replication because I can't learn all that right now. So why aren't people doing this? I submit it's because it doesn't exist. The only thing you could do is you could go ahead and get an iSCSI appliance and put it outside or you could have an NFS server, very popular to do it with NFS. However, the performance penalty you're going to pay there is going to be huge. It's not going to perform like local storage. And that's the whole key.
Can you do something with spectrum scale, something like that, a shared file system, and just have it?
Absolutely. Spectrum scale, we actually like GPFS an awful lot. It's great, but its latency on transactional loads is not fantastic, to say the least. You're going to get up into multiple milliseconds rather than microseconds.
And the efficiency of spectrum scale. Spectrum scale, you can only use one entire device. You can't slice devices. With us, you can.
So we're getting our results through, so I can stop babbling now. I'll just tell you about these. And you can see, this is the performance you expect from a local flash device. Average reads are about 104. This is, by the way, this was just a single thread, single queue. I'm not going for big numbers. I'm trying to see what the latency is for individual transactions. So 100 microsecond, 105 about for reads, about 20 microseconds for writes, 500,000 IOPS if I push it for reads. And right now an artificial 152,000 IOPS for writes. These drives are only spec'd at 50,000, so that's a bogus number. It means it's not preconditioned. So we're getting, a lot of the writes are completing in the device's memory cache. Again, I said we don't cache, but the individual devices are power fail safe, and they do have a cache. So you're getting that. So that's local performance. All right. So let's go ahead and, you know what, I'm going to skip this part of the demo. What I was going to show you was that I can do a Mongo database, put some data in, then I will kill the container. It will automatically move, which I'll show you anyway. I can show it to you a lot. The benefits of a live demo. So this is the volume that's mounted on that one host. I'm going to touch techlive-foo. You can see it's there. There is a file there. And of course now, if I go ahead and I kill, I'm going to go ahead and kill that pod. I'm going to do show pods. We were running on 20, where were we running before? We were 23, thank you. We were running on 23 before. You can see Kubernetes, I killed that pod. Kubernetes started up a new one on 22. If I do go into that host and cd/data/db, there is no techlive file. It started up another instance. Those other files are an empty MongoDB database, but of course, because I'm on a different host, I've lost that. So that's all I wanted to show there by showing you that this is possible with local, but you don't want to do it that way. So now I've just killed that replication controller, so I'm not running any more of those instances. All right. So let's show now the more interesting stuff. Now I showed you here on volumes. The only volume that's there is NVMesh volume. What I'm going to do now in Kubernetes is create a different replication group that's using a NVMesh volume, but one that didn't exist before. So there I just did it. I've got now a new one called demo. The container is creating, so it's actually pulling it off the network right now. And as soon as it starts running, there it's running. We should see here, refresh it for it, that I should have a new volume. There, I have a new test volume, another one that's 500 gigabytes, it's mirrored.
So
No.
creating the new job's great. has automatically created a volume.
If
And
they
you
don't
could
exist,
automate
yes.
The whole process.
Absolutely. The way this works is that if the volume already exists, it uses it and mounts it.
Right.
If it didn't exist, it creates it, puts an XFS file system on it, and then mounts it. So, but the key to show you is that this was all automatic, hands-off, just by Kubernetes commands. I was able to actually provision and use storage.
What are the limitations to how much your technology can be automated, driven by automation?
Well, of course, there are always limitations. But which ones did you have in mind?
I don't know.
Okay. We have an arbitrary limit on the number of volumes. Really, I think the limitations will come into operational limitations rather than actual technical limits, just on how much. For example, we can span over thousands of hosts, but generally you keep storage within one rack.
So how many transactions could you process per second, for instance, if people said, I've got thousands of nodes and I want to create 1,000 volumes every minute or every few seconds? You know, that's a silly example, but
I haven't measured the number, but our back-end management is also scalable. So when you hit when you hit it, because you will, in the example, you'll hit the limit of the one management controller. However, you can initiate multiple management controllers, and they send all the commands back to Mongo, so you scale the Mongo database, and you could increase your limit.
That's eventually consistent, though, I guess.
You might have to, the more transactions you do, yes, they'll take a little bit longer.
Yeah.
So, but it's definitely possible to scale both ends.
Essentially, this could be pretty much fully integrated within an orchestration automation.
That's the key. What you're getting is we're saying that we have a GUI, we have a RESTful interface, but we're demonstrating that this can be integrated into Kubernetes or Docker Swarm or Mesos. It's a matter of us writing the plugins. Kubernetes is the first one we went after. So I'm going to go ahead and I'm going to be on the wrong server. I think I typed,
Exit into the wrong window.
yes. There we go. All right, so I have no pods running again. Last time. Now let's do everything we're talking about. So you saw how it can automatically create a volume. Now we're going to use that existing volume because that has some of the data I want in it. There's one running on 23. And you can see here on 23, in this I have some different files here. I can do a touch, tech live, foo. Oh, it says tailive foo. I'm going to exit this, and then I'm going to do a kill that. Now I move from 23 back to 22. If I cd to /data, you can see that I should have my tailive foo file is still there, so that shows some not too exciting persistence. The key thing is this is an NVMesh volume. If I do a df dot, you can see that this is actually coming from dev NVMesh volume. You can see that matches here. Our volume list, if you look in the clients, you can see that the NVMesh volume is attached to node 22. And now I want to go into the FIO directory. And I want to run, this is the exact same tests that I ran on local volume. This is a series of 4 FIOs to show individual transaction latency for reads and writes, and then kind of bump up the IOPS and on both reads and writes. So this was complete soon. And what I want to show you here, hopefully, when this finishes, is that even though we're using a volume, now this one is running on 22. Kubernetes happened to give us node 22. If I go ahead while this is running, and I look at the volumes, and I look at this NVMesh volume, the definition, I can see that the drives, and I'll expand these. This volume is made up of one drive that's on 22 and one drive that's on 24. So it just so happens, luck of the draw, that I am using a volume, half of its mirror is local and half is remote. But it doesn't matter. They both could have been remote. The whole key is we get local style performance. So if you look at some of the results we're getting, you can see that before we were at 105 microseconds for read latency, and now we're at 110. Because I told you, we only add about 5 to 6 microseconds of overhead. So this is still local style performance. On write latency, we have added here almost 14 microseconds. Now, why is that so much more? We're doing a RAID 10 or RAID 1 volume here. That means every transaction has an additional lock, so that we actually a little bit more than double our overhead for RAID 10 volumes. But I would submit to you that a 34 microsecond write response time is still local flash performance. On IOPS, you can see I got, actually it's a little low, I got about 750,000 read IOPS, which is more than the one, because when we read, we're reading from 2 different drives. So that one should actually be a little higher, but about 750,000 IOPS. And for write IOPS, I got the 100,000 because I'm using these drives. Each drive is spec'd at 50,000 IOPS. So these are still actually a little over. It should have only been about 50,000, but because they're not fully burned in, I'm getting more than the advertised. The key is, by doing a RAID 1 volume, I got more read performance, because when we read, we alternate reads between the 2 drives. So you use that mesh there, okay? And we did that. All right, so let's do Mongo, show DBS. And these are actually Mongo commands. You can see Tech Live. I have some data in here. And that is totally wrong. There you can see I have a little bit of data in there. I'm going to go ahead and insert something else. Yeah, we've got this, or well, this I don't think they normally mean you to use it like this. No. And I did not terminate my string properly. Yes, this is kind of an example of what not to do. All right. So now if you see all this, we can see that we've entered now foobar. These are our entries. This is new data I just entered. I'm going to exit this. I'm going to exit this. I'm going to do something very silly maybe. So this is running on 22. I was going to show you a softer way to kill this, but we need to jump to the end. So rather than killing this instance very nicely with a Kubernetes command, I am just going to cross my fingers here. I'm going to log directly into the upper level of this node. And I am just going to do a tellinit 6, which for those of you who are familiar with Linux means I'm going to tell init to just kill this system, just reboot it. Not nicely, not shut down gracefully, just kill it. And there it goes. 22 is gone. If I now do a show pods, I have to type. Hopefully what we're seeing is that It still says it's on 22, which is not what I want to see. It may take a moment to realize that 22 is down. Ah, no, it's the same one. There we are. Okay. Sorry, that just took Kubernetes a little bit to notice that the pod was down. So if you now see, it's got 22 in an indeterminate state, but because it has noticed the container's not responding, it has spawned a new one on 23. Thank you. So now we will do. We'll go into that. It's not working. That's very interesting. The demo gremlins got me.
You should have sacrificed Tom to the demo gods.
I'm sorry. That is not. That is my error. There we go. All right, so now I'm on a totally different node, number 23. And if I go into Mongo and I do show DBs, I can see we still have Tech Live. If I do use Tech Live, and then go ahead and show all the entries. There you go. There's the data that we just put in live on the other machine. So, sorry for the little glitches there, but what we just showed is a machine died. We were using our storage. We started up a new Kubernetes automatically started up that container on a different host. That different host attached to it, and you can see we have the database exactly where we were when we were on the other host. At the same level of performance. Because I killed 22, you can actually see on the interface that I'm in degraded mode. This also, at the same time, showed that we had exactly what NVMesh is supposed to do. We had a mirror. The host that contained half the mirror died, but our volume continued working, and we're in degraded mode. When that volume comes back up, NVMesh will automatically rebuild the missing data. We do a partial rebuild, and it'll do that missing data only. So that's it. We just demonstrated that. You can have containers. They can be dynamically provisioned. They can move around. They get local flash performance. You have protection against a node failure. And in this case, we also ended up simulating a drive failure because the node that we killed also had the drive.
And a NIC failure.
Yes, and a NIC failure. So that's basically what we have for the demo. Last things I want to do is a little bit of myth busting. And we have 5 minutes or none?
We've got 10 minutes.
We've got
9.
Okay.
Sorry.
Well, you asked.
No hooking here.
Can I ask a question, please?
No questions. I have to get through. No, yes, please.
You mentioned the protection ring, and you got the new regulations coming out of Europe, etc.
Yes.
Can you do encryption?
We could. We don't today.
But that would.
So one thing we could do is we could use self-encrypting drives. It's a matter of where you want to do the key management. So that would give you encryption at rest. If you want to do encryption at flight, that's something we've considered, but we don't have it yet. But any of it's possible.
That would be very useful for the new.
Yes, anything is possible because we're doing the operation at the client. That kind of functionality, it's a great question, because how do you add encryption? Like if you start encrypting everything on a centralized box, you need really massive CPUs, you're going to restrict your bandwidth. But if I can encrypt at every single client that's sending data as it's sending it, maybe if I'm using up an extra core on the client, or using some acceleration, as other folks mentioned from Intel calls, I can really scale my encryption as well. So that would be the way we would add it, but we don't have it today. So ultimate scalability. I hope I've shown this. there are folks that are saying now that they can get our, this kind of level of performance, but they're basically one box. And one box is always going to have a limit. It doesn't matter if the box is 5 million IOPS or 10 million or whatever. It's still one box. We can go ahead, if you want to talk about scalability, we can scale to, we're in the iteration right now, 1024 nodes. You can have up to 60 drives per node if you want, which means that we can get up to 2.5 billion IOPS in one cluster. Please don't make that the thing you tweet. Please tweet about Kubernetes and whatnot. The fact that it's scalable, that it's all automatic provisioning and whatnot. But there are people out there saying that you can't scale this. You can't scale this at the client. Yes, you can. We're doing it.
Would the E8 be on the right-hand side of the screen?
I don't know. Maybe they could. That doesn't look like their box, but it looks similar to their box.
What tease you are?
Well, this is a super micro box. I believe they use an AIC box, so it's completely different. But it's one box. What do you do if you want to spread a volume over multiple boxes? You have to do something in the client anyway. You have to go back to software RAID, MD, Atom, LVM, something like that. It's a nightmare. We take care of all the logical volume management for you. We also notice people are talking. People are talking to certain people in this room. And some of the quotes that they said that about us, they threw us in with some other folks, but they said about Excelero was, if you're only accessing NVMe drives directly and running software on clients to manage it, which is what I told you about, you can't natively share block storage volumes across hosts as a result. This is 100% wrong. Our product has been designed from the day one for multiple hosts to be able to attach to a logical volume just like a SAN. It looks like a SAN, it operates like a SAN. NASA Ames, one of our very first customers, has 128 clients. Each one has a single drive, and they made a massive 256 terabyte flash drive that they put a CXFS file system on. Every single client attaches to that, and every single client gets local flash performance. We support multi-reader, multi-writer on our logical devices. You can attach them to all sorts. So you can share block devices on our system. The other one is they said you can't really separate compute and storage in a way that allows you to scale them independently. And that also is not true. I told you we don't use any CPU on the targets. So you can do this. I'm going to see if I can get in just 3 minutes.
You've got 5. Sorry, 4.
It's still 5.
It's 5?
Yeah, I'm fine.
All right, so what I'm going to run real quickly is a big FIO job. This one's 56 threads, queue depth like 16. It kills the processor on the system. I'm not trying to get you the best performance number here. I'm just trying to drive CPU up. Now, if you look, although one drive has failed, this will be interesting. So test volumes, the surviving NVMesh is on 24. So if I look at the CPUs, you can see this is where I'm running the load. CPU load is going up, doing a massive read IOP load on 23. This is where I'm running. This is the host that contains the surviving drive out of the mirror. Do you see no CPU? Because it's not using any CPU. We're not using any CPU on the target. Okay, it's getting, if you look at this job right now, it's getting 550,000 IOPS served by that host, but that host is not expending any CPU. Well, that's interesting. Yes, 24 is not using any CPU. So, going back to this, why is this important? Because it was said you can't do this. You can't, in a converged model, the statement was made that you can't separate compute and storage, except with NVMesh, you can. We logically disaggregate that. Because we don't use any CPUs, you can scale storage independently. You can put it in the nodes, you can put it outside the nodes. You can scale your storage completely separately from your compute. You have the freedom to do that, whether you do a converged mode or disaggregated.
So what do you find results in contention for that data, for example? What's the corner cases that would result in, say, performance contention, degradation across the mesh?
So where we hit limits are bandwidth on the network on a regular basis. I'm using a 56 gigabit Ethernet connection today, which I know is weird. That's a Mellanox thing. You can use 25, 100, it doesn't matter. But we tend to hit network limits. If you spread your volumes out appropriately, you actually get a lot better performance and spread them out. To be fair, what you said earlier is also true though. If you continuously create breakdown, we could start using different segments and you could end up with an over allocation of segments on one particular drive. And that's possible you could hit that limit of that drive.
Are your customers going to be spending more on networking devices as a consequence of distributing and storing?
No, because if you look at the cost per port of a 100 gigabit switch from any number of vendors, Mellanox, Arista, Cisco, all these folks, or any of the Broadcom-based ones, the per port price is so much less money. You can buy some of these switches, Supermicro, I'm not trying to promote Supermicro, but they just sent out a notice to us and said you could buy, was it 5? You could get, if you bought 2 switches, you could get each one for I think $5,000 US for a 32 port 100 gigabit switch that could be used in this environment. Please tell me how much a 32 port fiber channel 16 or fiber channel 32 switch would be. It ain't going to be close to $5,000. Even if you have to put Cumulus on top of this and to get
Let me ask the question again.
Yes.
Are your customers going to be using comparatively more networking devices than others that don't?
They will if you only consider Ethernet, because let's put it this way. If you're using 10 gigabit Ethernet today and fiber channel 16, you have about 26 gigabits of bandwidth between your storage network and your data network. If you move to 25 gigabit networking, which by the way is the same price or less than 10 gigabit, you now have about the same bandwidth. You could run totally network converged, and in that case, as long as you had an upgrade planned, you wouldn't necessarily be using more ports or more equipment. If you chose to do a separate storage network, your Ethernet network for storage would be replacing your fiber channel network.
How many ports of networking do you recommend per terabyte or petabyte of?
So we can get about 1.25 million random read 4K IOPS out of a 100 gigabit link, and about almost 12 gigabytes per second. So that's your metric. So if you match your NVMe drives to that networking, that tells you how many ports you need.
Happy to share in the coffee break a couple of customer examples.
Quick curiosity, you mentioned 2 models of working, one with a NVMe box, another with the local storage. Can those 2 be combined?
Absolutely.
Are there any issues with combining?
Nope, we don't. We fully allow you to combine them. Your problem would be you would be oversubscribed maybe on the 24 drive box, but you'd have more drives and bandwidth available than you can get out of the networking interfaces. But we do allow you to mix them, and our provisioning stuff, our policy engine, would actually let you limit how you grab segments out of it.
So there are efficiency advantages to actually distributing the NVMe ones.
You get the highest levels of aggregate performance by doing converged and distributing. However, you get the best dollar per gigabyte for capacity if you do the 24, especially if you use a read optimized drive.